And we're off. So we have handouts. I have a power supply for my computer. I was having a bit of a messed up day yesterday. And I was a little freaked out because I thought we had to get through the entire lecture 4 this week, but we're only doing half of it. We're going to do the second half next week. Because there'd be a lot of confused people if we had to do the whole thing. This is a warm-up for next week's material, which is Thevenin equivalence, which is real challenging. One of the challenging parts of the class, most challenging parts. I think you get the most complex problem-solving techniques involved. But that's not until next week. So this week we're just focusing on these two topics of linearity, which results in superposition, and a couple other nice benefits. Superposition, which we did yesterday, is all about the way you can take a circuit with multiple sources and turn off the sources and find the effect of each source at a particular point in the circuit separately, and then add those together because it's linear, right? Because it's linear. Before we dive into source transforms, anyone have any other thoughts about this or any questions? Anything else about the class that we're looking at? I may have to move my quiz back a little bit. I think my quiz covers Thevenin, so quiz 3 might be another week or so back. As I mentioned, superposition is a nice way, like if you really, if you get good at it, you can just solve a circuit by inspection, because it's usually some combination of voltage divider and current divider to solve it. Of course, if you have a dependent source, it gets a little more challenging, but even that isn't really that hard. Solving each of those separately isn't really too hard. In fact, solving that whole thing really isn't that hard either, right? Like if you didn't have superposition, you could just do 1 kVL and find the answer, right? Did you see that? So this one actually is sort of an easy circuit. You can do this by inspection without doing superposition, right? You just do 1 kVL. You could just do kVL with this 2 amp source, okay, and leave that 4 volt source on there, and just, the final, alternative kVL of the whole thing. Original circuit says that, -4 plus, well, you're going to have 2 amps going there, right? Plus, minus 2 times 10, right? Plus 3 VAB. Go away. Wait for this thing to go up. So minus 2 times 10, right? Because of the signs here. Plus 3 VAB plus VAB equals 0, and this will get you the whole thing. But doing it this way doesn't give you the insight of, like, which source is providing more, is contributing more to VAB. It doesn't give you that kind of internal view of the influence of the different parts of the circuit. So anyway, so superposition is kind of nifty, and you'll find it helpful at certain times. And then this one, the next topic, source transform, is sort of our lead up to Thevenin equivalent circuits, which we're going to do next week. So source transforms are another way of looking at a circuit, which allows you to sort of simplify. Mason kind of was alluding to this when he asked if do you have to worry about, when you're doing a circuit like which has these terminals here, do you have to worry about like what comes after that, or is it independent of that? And the answer to that question is yeah, you can take parts of the circuit and remove them and simplify them. If all you're worried about is the performance of the circuit at 2 particular terminals, like in this case A and B, it's possible to transform circuits from one form to another, which allows you to simplify things and gobble and gradually simplify large quantities of components into a single source with a resistor. And the basics of source transform is converting a voltage source in series with a resistor to a current source in parallel. You can find a way to make these equivalent so that at the terminals A, B, they look the same. And what I mean by that is if you put a box around these two different circuits, oops, and all you're doing is connecting something at A, B to it, like a load or something. You can define these the values of these sources and resistor values such that the load is going to experience the exact same current. You know, whether you hook it up to one circuit or the other, you can define these so that they're actually equivalent circuits, so the load doesn't tell the difference. And that's a powerful tool that we can use to simplify things. The idea is we should have sort of an equivalent like current for any load attached to AB, and any load attached to AB. And so RL can be anything from 0 to infinity, or that means from short circuit to open circuit, right? And we can look at the extreme cases to kind of find out, what that, how those these two circuits can be related, so that that actually happens. The extreme cases would be like the short circuit case, where RL equals 0. I should be a doctor. My handwriting is just terrible. And when you have a short circuit attached to this guy, right, that means I'm going to erase that. Actually, I'm just going to draw these separately, and then here is our current source. Those are the two circuits, so you want them to be equivalent, right? And we want them to be equivalent when we have a short circuit connecting these, and we have this current I going from one terminal to the other. We want those to be equivalent. We want to have the same current I, whether we have a voltage source in series with a resistor or a current source in parallel. And this is R, and that's R there. So when you look at these two circuits, you can find in the first circuit what's I. V over R, just Ohm's law, right? Vs over R. And in the second circuit, what's I? Yeah, in this case, I is just Is. So if we want these things to be equivalent, we have to equate these things. So Vs over R has to equal Is, or Vs would have to equal R times Is. So in other words, if you could choose the current source or the voltage source, you could choose it such that this is true. And they have the same R's here, right? So this R is the same as this R. But if you just choose the value of the voltage source or the current source, you could make those have the same current if you have a short circuit across those terminals. They'll actually be the same, right? So you wouldn't really know the difference of what's inside the box just by looking at the current there. You couldn't tell the difference. And then the question is, well, does that also apply when we have an open circuit there, right? So with an open circuit, again, we're going to have our resistor, our voltage source, and we want this to be equivalent with the current source in parallel with the resistor. And these terminals, which are AB, we could imagine, this voltage VAB here. Now, in the open circuit case, there's no current flowing, so there's no point in trying to figure out current there. But in the voltage source case, what's VAB? Zero, right? Why zero? It's an open circuit. Is the voltage across an open circuit always zero? Mark says no. What were you saying, Mason? Oh, so I'm asking the question is, what is VAB when we have an open circuit from A to B on the circuit on the left? We're looking at you have a voltage source, we got a resistor, and we have an open circuit. And the question is, what is VAB? Omar? Is VAB a supply voltage? Well, it's the voltage, like if you hook up your voltmeter to those terminals AB, what would you read? What would you expect to read? Mark? VS. Matthew, what do you think?
Well, I feel like it's zero. There's no current.
It's zero because there's no current flowing. Pong, what do you think? You think VS. Daniel? VS. Alex? 70? Zero. Cool. So it's about maybe what, 5 zeros to, or 3 zeros to 5 VS's or something like that. Okay, how can we prove it? It's one thing to assert it, but how do we prove it? Mark? Kirchhoff's voltage law. Okay. When you have an open circuit, it's true something is zero, but what's zero with an open circuit? The current is zero, right? So the current through R is zero. So there is no current here. So if you talk about the voltage drop across R, what is it? Zero, right? Ohm's law says, V equals R times I is zero, so V equals zero, right? So KVL says minus VS plus zero plus VAB equals zero, right? So KVL, let's just write this out because this is really important. These extreme cases really throw people. And you have to realize that in circuits, your gut, which you've relied on for so many things in life, is going to probably be wrong. And so you have to doubt everything your mind's. I had a student last semester who was just an abundance of confidence and would just go down the wrong path, and just be completely convinced that he was right. And it's good to be confident, but in circuits, it's very humbling. And you have to be willing to accept that your gut is wrong sometimes. KVL says, I do this. It happens to me all the time. It's just endemic in circuits. It's complicated. It's not intuitive. So KVL says minus VS plus zero plus VAB equals zero, right? Going all the way around that loop because zero is zero times R, right? So VAB has to equal VS when you have an open circuit. There's no current going through that resistor. There's no voltage drop across the resistor. So the voltage at that open circuit terminal is going to be the same as the source voltage. So VAB equals VS. And this should be equivalent. We want this to be equivalent in the case of the current source in parallel with the resistor. What's VAB in the second circuit? ISR. Yeah, because all that current from the source, current source is going through R. And VAB is essentially measuring the voltage drop across R, right? So VAB equals R times IS, or IS times R. So that's VAB, and these will be equivalent when, again, VS equals R times IS. So interesting, isn't it, that VS equals R times IS again. And that's in the extreme case, but we can make the argument that for any arbitrary R, and we're going to do that in the next slide, that these two will be equivalent if we choose the VS such that VS is defined as R times IS, or we choose IS such that IS is VS over R. Then we'll actually have equivalent circuits in both of those cases. Matthew.
So does that mean like anything with the voltage source, you know, circuit? So like you're like if it's simple like this, and read whatever the plus is.
Yeah, it's exactly what I'm saying. If you take you could do this in the lab. You could take your voltage source, your 12-volt source, and hook up a resistor in series with it, but have an open circuit and put your. Gosh, we should do that, right? I never do that in the lab. I mean, you're going to have opportunities to sort of do that, but that's something that is just really hard to get over. But once you realize there's no current flowing through R, there's not going to be any voltage drop from that. So it's going to read the same as your source voltage. Yeah, Mason? The two ISs are the same, yeah. I mean, the point is, although I have a lowercase is here, I should have drawn that as a capital IS. This IS is here. It was a lowercase is up here, so I kind of messed it up. Yeah, IS is the same throughout that whole slide. I should probably just make this a capital IS. In case you're confused by that, make that a capital VS. Yeah, you could easily do this in the lab. If you think about it, next week we're going to be doing. Actually, we're taking interlude because it's taking us. We're not going to get Thevenin until next week, so we're going to be doing experiments with diodes and transistors next week, and just a little stuff to kind of play around with. You could actually try that for the voltage source. If you remind me, I will do that. I remind myself. I forget though. Let me know. But again, we're going to prove this once and for all now for an arbitrary load resistor. So we have voltage source. We got our resistor. We've got, we want to see, is this equivalent? We've got a current source. Resistor. We want these things to be equivalent. And the thing we're doing is we're now going to add an arbitrary load resistor to see if we get the same current going through it. So if we can prove that we're going to get the same current going through the load resistor when it's any value that you can think of, then we've basically established the equivalency, the full equivalency of these two circuits with each other. In the first circuit, what is IL? Right? Yeah, it's VS over R plus RL. Okay. What about the second circuit? It's a little more complicated. What tool might we use to find IL in the second circuit? Current divider equation, right? Says IL is going to equal 1 over RL over 1 over RL plus 1 over R times IS. Now we can do a little bit of manipulation if we take and multiply top and bottom by R times RL. And clean things up a bit. you're going to get R over R plus RL times IS. Which will equate, these will be equivalent because, or we can make them equivalent because we want to make Vs over R plus RL equal to, R over R plus RL times IS. And these will be equivalent if we multiply both sides by R plus RL if Vs equals R times IS. Again, once again, that's the requirement for them to be equivalent. If you do that, the current through the load, RL, is going to be the same. Whether you have the circuit on the left or the circuit on the right. The load won't be able to tell the difference. And this gives us a powerful tool to simplify things. Just like in statics, I think about this as an analog to statics. When you have a complicated system of forces and statics and you want to reduce them to one equivalent force in a couple moment or something like that, right? Well, in circuits, you can reduce a complex network of circuit elements into a single source and a single resistor. And the advantage is, of course, it makes it a lot easier for designing things. When you can kind of simplify large chunks of circuit and just say, well, this circuit, this whole stuff here at this point is just going to look like this and this, and then you can solve things, do things a lot more easily. So again, here's the explicit relationship for independent sources. You have a voltage source in series with a resistor, current source in series with a resistor. Vs equals R times Is. They're the same if that's true. And for dependent sources, again, if it's a voltage source, some kind of controlled source, you can even do it with these guys, but there is some stuff you have to be careful about. I think we'll get to at some point. Vs equals R times Is. Okay, so we're left here with example 3. Find the current in RL using source transformation. So again, we have a circuit here which has two sources. This is another symbol for a voltage source. This thing here, right? You see that? And that's a specific kind of voltage source. I think I talked about it. What kind of voltage source does that represent? It's a symbol typically for a battery. And you might see them with several, it indicates, it represents like a single cell of a battery, and you know how you can stack up batteries, like your 12-volt battery in your car. If you actually open it up, it has like a series of 2-volt cells that are kind of stacked up. You got 6 of these 2-volt cells stacked up in series that gives you 12 volts. So you can see them kind of sometimes with a couple layers of those things, but in its simplest form, this is a battery. And it's saying it's a 5-volt battery. And you've got a 4 ohm resistor, a 6 ohm resistor, 2 amp source, and this load resistor. And we're asked to find out what is IRL, the current going through the load resistor. Now, once you get good at source transforms, it's easy to take, and these are actually nice tools to simplify the circuit a little bit. If you can do an easy source transform, you can reduce the number of components. It simplifies what comes next, like nodal or mesh, or you can make things a little bit easier. I tend not to use it too much. We tend to kind of go towards the big, heavy tool, which is nodal analysis, but this is actually a nice tool, and it leads us to an appreciation of Thevenin equivalence. The way you actually apply source transforms is you look at the circuit and you see where do I have a voltage source in series with a resistor, or a current source in parallel with a resistor. Do you see those in that circuit? So you can see the 5-volt source is in series with a 4-ohm resistor. So you could circle this thing and you could transform it. You also can see you have a 2-amp source in parallel with a 6-ohm resistor. So you could transform this into a voltage source in series with a resistor as well, in which case it would look, and I wouldn't write this because we're not going to do this transform until later, but you could turn this thing into a resistor in series with a voltage source. You could do that. I'm going to erase it right now so you don't have to put that down there, but it is something you could do. It just doesn't really help us at this point to do that transformation first, because then we're going to have 2 parallel branches of voltage sources in series with resistors, which doesn't really help us reduce it any further. But if you look at this, you can say, all right, well, this is a voltage source in series. So if I figure out, according to my formula here, if I find IS equal to VS over R, I could change that to a current source in parallel with that same resistor. So if I choose an IS equal to a 5-volt battery over a 4-ohm resistor, which is basically 1.25 amps, what we're saying is that these terminals, if you call this, if this is like the AB terminal of this previous example, these AB terminals, you can just say, well, I'm just going to, at that point there, if I'm only concerned about what's the current through that load resistor, which is a distant part of that circuit, it doesn't really matter whether I use a voltage source in series with a resistor here or a current source in parallel. It's going to have the same effect over on the other part of the circuit. So, and that's going to be in parallel with the 4-ohm resistor. And then what that means is I replace that circuit, that part of the circuit, with a 1.25 amp source. And I move the resistor so it's in parallel. It's kind of messy to see it that way, right? But I'm just transforming. You can visualize that in your head. You're just transforming that voltage source in series to a current source in parallel. And then just to keep us from getting confused, we're going to redraw the circuit with that in place. But in the process, we could do another slight modification to make things a little more understandable too. So in other words, I have this 1.25 amp source now, which used to be a voltage source, now a current source. And it's in parallel with the same R, which is 4 ohms. Well, actually, can you erase that real fast? Sorry. Just a small tweak here. If you look at it, right, if you got 4 ohms here in parallel here, this 4 ohms is actually going to be in parallel with 6 ohms, right? And do you think there's any difference if we actually move this 2 amp source so that it's kind of sitting right next to that 1.25 amp source? We're still pumping current through the same 2 nodes, right? My point is, do you think this is okay? Should this be okay to just move that 2 amp source right next to the 1.25 amp source? That'll help us in sort of in our next step, kind of simplified even further. And then that 4 ohm resistor now comes over here next to the 6 ohm resistor. And then we have our RL here. Anyone have any questions or any issues with that? There's no reason why, if you have 2 current sources pumping current between the same 2 nodes, you can't, move them so that they're right next to each other, right? Do you agree? They're still doing their job. We're not changing anything, right? Changing the arrangement of those 2. And then that allows us to see that, oh, well, we might as well just combine those 2 together. If you've got 2 current sources pumping, a different amount of current from one node to the other, why not just add them together and just call them a single current source, right? That simplifies your circuit again. So, we can start to kind of put circles around this thing and just say, well, yeah, let's just call this one thing. Let's just call this thing another thing. And then therefore we're going to have a total IS, which is going to equal to 1.25 plus 2, which is 3.25. And a total resistance here of 4 parallel 6, well, at least excluding RL for now, which is 2.4 ohms. So now we are able to draw our circuit in a much simpler form. Okay, isn't that nice? And at this point, you could use the current divider formula and find the current going through that load resistor, but that's kind of complicated. You got to do those reciprocals of those resistors. Why not just do another source transform one more time and turn this current source, which is in parallel with a resistor, into another voltage source, which is in series with a resistor. So to do that, Vs would have to equal 3.25 times 2.4. But you could, and you could redraw the circuit one more time, having made that transformation, and then now you're going to have a voltage source, which equals the product of those things. I don't know what that is, 3.25 times 2.4 in series with a resistor that's 2.4 in series with our 8 ohm RL. And so now by inspection, we can find that the current going through that load resistor IRL is just going to be the voltage source, this transformed voltage source, divided by the sum of those two resistors. And the arithmetic just sort of falls out from there. So a nifty tool can help in a lot of situations. Again, we're just learning these additional tools. Superposition was one of them we did yesterday. This is source transforms, getting us thinking about equivalent circuits. These are equivalent, at these two nodes where they are connected to the rest of the circuit. The rest of the circuit doesn't care if you replace them with one or the other form of those two circuits, as long as they have the same equivalent behavior at those two terminals, A and B. Alex? So two current sources in parallel, you add them as if they were like two resistors in series. Yeah. It's not quite the same analogy because resistors, but yeah, you just add them up. They're additive because basically, again, think of like the water model. If you've got a if you have some kind of a pump or a water fountain in your home, right? People have those things to kind of help relax. They just pump water up and they kind of trickle down and make a nice water noise, right? And maybe you have two pumps, in that system because you want more water. You want a louder fountain. So the first pump, is giving 1.25 gallons per hour. The other one's doing 2 gallons per hour. You're going to get a net flow of 3.25 gallons per hour gushing down your waterfall, right? That's the analogy. The water analogy comes in handy in a lot of these situations. Just kind of justify it. Doesn't have to be some abstract thing with electrons. Okay, so yeah, the next one is we're going to solve a circuit problem using a dependent source using source transform. So this is where we'll see how you can do it. And there is a caveat with these, which I'll explain, and then that's pretty much it for this week, and we'll do some practice problems tomorrow. So we're asked to find Vx using source transforms. Vx happens to be, in this case, the control voltage for a dependent source in that circuit. But when you look at that circuit, you'll see that some things should kind of stand out, right? Where do you see any transformable elements in that circuit? What can we transform? Mark? Yeah, you could transform this again into a current source in parallel, and you could transform this into a voltage source in series, right? And if we do that, let's see, we're going to have, let's look at this thing. So in this case, the transform would require a current source that has an IS of 6 volts divided by, right, it's Vs over R. So it's going to be 6 volts divided by 2, which is going to be 3 amps. And up above here, you have Vs, which is going to equal an R IS here. And we have an R, and we have a current source that has a current of 0.25 Vx. A little confusing when you have a voltage-controlled current source, right? The Vx is controlling that current source, though. There is some unit conversion with that constant 0.25. So IS is 0.25 Vx. So Vs has to equal, the voltage source equivalent for this thing would have to equal 4 times 0.25 Vx. And that means it's just Vx. Oops. Mason? Why would you do both? Well, I think you can see that if you do the transformation of this source, actually, let's look at the next example. The next part of the circuit is drawn below here, right? So you can kind of see that when you do the resistors here in parallel, you can actually gobble those up. And then you would have, you can kind of see by looking ahead, right? Then you have these things in series. That makes it a little bit easier to analyze. If they're still in parallel, it becomes a little bit cumbersome to kind of deal with that circuit when they're parallel like that. Whereas when you finally have it as a single loop here, then it becomes a simple thing to analyze. Right? Let me be honest with you. I really want to caution, source transforms are really effective, but when you have dependent sources, you can really screw things up if you're not careful. And so I kind of, because of that, I kind of recommend people not using source transforms when there's a dependent source involved. And I can explain that after we solve this. One of the pitfalls that can take place with source transforms when you're doing them with dependent sources. But right now, this is gonna actually work out, and we can see that our we could combine these two resistors and turn them into a 1 ohm resistor because they're in parallel, and then we could turn that source, that current source, back into a voltage source because we would take 3 amps times 1 ohm, right? And you can sort of see that if the Vs is 3 amps times 1 ohm, you're going to get a 3-volt source. And so, and then you can move those parallel resistors back to this point right here. You got the 1 ohm, you got the 3 ohms. But weirdly enough, and this is actually important, this actually gets around the fact. This is sort of where things can kind of go weird. You notice how the 1 ohm resistor went up here, but the Vx stayed between those two nodes. The control voltage is not really it doesn't go with the resistor. It has to stay between those two nodes. So you can't mess up those two nodes, right? The two nodes here, which I'm going to call these A and B here. These things have to be left alone because that's the two nodes that Vx is being measured across. If you gobble those things up, like by combining the 4 ohm and the 1 ohm resistor, you've lost any way of determining what Vx is. You know what I'm saying? And that's why it gets kind of confusing there. You see how you could easily make a wrong turn here. I wouldn't require you to use source transforms ever on a circuit that has dependent sources, just because I'm really worried about all the implications of that. Isaac. Can you still measure the voltage across two nodes even though there's no branch or element? Yes. Can't you just hook up your voltmeter in any two nodes in a circuit? It's the difference between the potential difference between those two nodes. That's what your voltmeter is going to tell you. It's really easy to do. And in fact, your voltmeter actually is a tiny load on a circuit. It's like a really high resistance. If you hook up a voltmeter to it, don't draw this, and just sort of. It's like a 1 mega ohm resistor, or attached in your voltmeter to kind of measure that voltage. So it's not putting much of a load, but there is a little current going into your voltmeter when you do that. So you're influencing the circuit a little bit, but very little bit. Right, so we never want to mess up by combining those two, because then we would lose any sense of what Vx is. These two 1 ohm and 4 ohm resistors, they cannot be combined. But we do have a point where we could analyze this circuit pretty easily. And in this situation, you can find, using KVL, you can do KVL around this part of the circuit. And you can do KVL around the whole thing. So around the whole thing, you can just say, oh, well, okay, -3 plus 1 times I. You've got some I. You've got a single loop there, so you have 1 times I plus 4 times I plus Vx plus 18 equals 0. But you have two unknowns in that circuit, right? So you have an I and a Vx in that. I mean, two unknowns in that equation, I and Vx. So you can't really solve for that yet. But if you did the second loop, you could say, well, okay, well, also -3 plus 1 times I plus Vx equals 0. And you can solve those two for I and Vx and find the answer. Certainly you could do it. Just got to be careful. I'm much more comfortable using source transforms when it's just dependent sources involved. Isaac. When you combine the two parallel resistors, why does the resistor jump to the top branch? Because of our earlier derivation, which you missed. Unfortunately, you're going to have to watch the video, which basically says the source transform, we can make these equivalent circuits. We can transform a voltage source in series with a resistor to a current source in parallel with a resistor, and vice versa, if we establish Vs so that it's R times Is, or you establish Is so it's Vs over R. You can make those changes in the circuit to simplify things if you adhere to this rule. And you can see the resistor here was parallel, and then it becomes in series to flip from one to the other. It's parallel with a current source, and it's in series with a resistor. It's in series with a voltage source. Well, you can certainly combine parallel resistors anytime like we did right here. That's totally fine. Yeah, but your question was, why did that end up here at 1 ohms above there? It did that because we turned that current source into a voltage source. That's a transformation. And that transformation requires you to move the resistor so it's in series with the voltage source. Mm-hmm. Right. It's a two-step process. Mason.
I would have thought that you do one loop to the left of Vx and one loop to the right of Vx.
Yeah, could you do one loop to the left of Vx and one loop to the right of Vx? Yeah, you sure could. Yeah, that's because that's what my slide tells me to do. But you know what? There's no reason. Why don't we call this loop 1? and redo our equation for 1. It'll work the same. The point is you're getting enough information so that you have different equations so that you can solve them, right? And doing it for just loop 1 there on the right would just be, minus bx plus 4I plus, oh wait, maybe not, plus bx plus 18. Well, actually, that helps us solve for I, right? The x's cancel out, and basically I equals 18 over 4. That's kind of nice. And then you can just plug that into the second equation and find out what vx is. Yeah, good questions. Like I said, I don't use them a lot, but applied sparingly, they're actually kind of helpful. And this equivalency of circuits leads us to a broader, more powerful theory, Thevenin equivalence, which we're going to explore next week. Yeah, 70? I advise you not to. Just be aware of that. Just because look at how we had to sort of be careful about that. It would have been, it would have been tempting, and my naive approach would have been to say, well, if Vx is the voltage across that 2 ohm resistor, and we transform that into a 1 ohm resistor, don't we have to put Vx over here? Doesn't that kind of make sense? Wouldn't you sort of think that the Vx should sort of follow the resistor? But it doesn't. It actually it adheres to those 2 nodes, right? And if you're aware of that, it's just a little more complicated to keep track of that, right? If you're aware of that, it'll actually work out okay. I've just seen people mess up source transforms when they have dependent sources because they move like the Vx over here, and then that doesn't work out the same anymore. And other current dependent sources have currents as the control, and again, you can't mess with those things because it's going to change the relationship of the dependent source and the dependence to the current, to the dependent source and all that. So yeah. So anyway, that's basically it. I actually at one point made an assertion that we should have a thing called Rebold's rule, which is never transform a resistor that's has a control signal involved with it when you're doing source transforms. And here, actually, they're doing it, but carefully, so that we keep the same sense of what the control signal is. Right? If you change that, then it messes up your dependent source. But we only have 3 minutes. I think this is probably a good enough place to stop. Tomorrow we're going to do some practice problems. Really important to do those. I recommend everyone showing up for that, because this is the stuff where it gets to be like the most challenging part of the class right now the next 2 weeks. And then we go into op amps, which are easier, and some other things get easier initially. And then we go back to this stuff again when we're looking at AC circuits. So Thevenin and source transforms, all this stuff comes back, only with complex numbers at the end of the class. So you really want to get this stuff down solid the first time so that it's easier the second time. Yeah, Isaac? Will you be implementing phasor diagrams? Well, not really phasor diagrams, but phasors will be used to understand AC circuits. We'll be using phasor transforms to solve AC circuits, which transforms a sinusoid into the complex domain. And I, this square root of -1, which just seems so mysterious, is going to all of a sudden take on a new meaning as a 90-degree phase shift for a sine wave. And it's brilliant when you see it that way, because it makes a lot more physical sense to think of I as a 90-degree phase shift than to think of it as the square root of -1. And we'll see that later. Okay, we are, I guess, out of time, a minute early.